Okay, the last thing I want to show you as far as solving systems of linear equations is not another method. I mean, we've already learned the graphing method and the substitution method and the equation addition method. And then the one that I think will be the most useful to you going forward, this newest one, this Gaussian elimination method. I'm not going to teach you another method. What I'm going to do is more Gaussian elimination. But before you just stop the video and like, I already learned that, I'm good. We're not going to do Gaussian elimination in two variable systems of linear equations. What we're instead going to do is Gaussian elimination when we have three variable systems of linear equations. So instead of just x's and y's, we have x's, y's, and z's. And instead of two equations, you start out with three equations. It'll make the process a little bit longer, but the good news is the methods that we learned up here for Gaussian elimination will be the same methods that we use down here. We still have the exact same tools. We can interchange rows, we can scale rows, and we can sum rows. And our goal is still to get the matrix into a diagonal form. It'll look a little bit different because now we have three variables and three equations. So instead of our matrices having 2 rows and 3 columns, they're going to have 3 rows and 4 columns. A column for the x's, a column for the y's, a column for the z's, and then a column for the constant. Much like we couldn't create our matrix until the equations were rewritten in a specific form with 2 variables, that same thing is true with 3 variables. The form that you're looking for in 3 variables is just like the form you're looking for in 2 variables. You want all your x's, then all your y's, then all your z's equals some constant. So we're lucky enough to have this system given in the appropriate form. And in this other example that I think was supposed to say 9z here, not 9, it's also written in the appropriate form. But maybe when we get down to this example, we'll have some manipulation to do. Anyways, my notes say that I'm supposed to do this one first, so I guess I'll do this one first. First step, let's rewrite these systems as a matrix. So the coefficient on the x is a 2. The coefficient on the y is a -2. The coefficient on the z is an implied 1. And the constant is a -2. So my first row is 2, -2, 1, -2. For my second row, I'm going to have -4, 7, 1, and 13. And for my third row, I'm going to have 6, -3, 9, and 6. Instead of my goal being to create a matrix that looks like this, where I have 1s on the diagonal, my goal is going to be to create a matrix that looks like this, where I have 1s on the diagonal. And guess what? If we had a linear equation in 4 variables, which we won't in this class, but is entirely possible, what we'd be trying to do with Gaussian elimination is create a very similar looking matrix with 1 more row and 1 more column and the 1s on the diagonal. So how are we going to turn this into this? Well, it's the same process as before. Let's start with the zeros in the first column. So these zeros here and here. We're not really worried about this top row, so maybe we'll just leave that alone for now. 2, -2, 1, -2. But we do want to create a 0 in this spot. How can we create a 0 in this spot? Well, I can take this row and I can add 2 times this row. Because 2 times this 2 gives me a +4, and -4 plus +4 gives me the 0 that I want. 2 times this -2 gives me -4, and 7 plus -4 gives me +3. 2 times this 1 gives me 2, and 1 plus 2 gives me 3. 2 times this -2 gives me -4, and 13 plus -4 gives me +9. Our next step is to get a 0 in this position. And you could probably do it the way things are written right now, right? You could be like, I want to take -3 times this first row and add that to this third row. And that'll absolutely work. However, especially when these are new, it's so easy to make a mistake. You might notice that all of these numbers in this row are divisible by 3. It's not a terrible idea to divide everything by 3 before you do that step. Instead of a 6 here, I can make it a 2. Instead of a -3, I can make it -1. Instead of 9, I can make it 3, and instead of 6, I can make it 2. By doing this scaling before I get a 0 in this spot, I think it'll be easier to get a 0 in this spot. I'm good with the top row. I'm going to leave that completely alone. I'm good with the second row because I have a 0 where I want it, so I'm going to leave that completely alone. And then I'm going to replace the third row with the sum of the third row and -1 times the first row. In other words, this minus this. 2 minus 2 gives me 0. -1 minus -2 is the same as -1 plus 2, which is +1. 3 minus 1 is 2, and 2 minus -2 is the same as 2 plus 2. What I've come up with is a matrix that has zeros in all the appropriate spots in the first column. So now I move on to the second column. You might notice that we're trying to get a 0 up in the top row and in the bottom row of the second column. But don't worry about the top row for now. Just worry about the bottom row. This didn't really matter up here when I only had 2 variables, but what you want to do here is get zeros in the spots below the diagonal first. And it helps to go left to right. So kind of think, in my first step, I'm going to get zeros here and here. And then in my second step, I'm going to get a 0 here. And then after I've gotten all those zeros, I'll worry about the zeros up above the diagonal. So how do I get a 0 here? Well, it's a little bit hard the way things are written, but you might recognize that in my middle row here, all of the values are divisible by 3. So I could, if I felt like it, divide all these numbers by 3, leave the first row completely alone, but take the second row and replace it with 1/3 times the second row, so 0, 1, 1, 3, and then leave the third row alone, 0, 1, 2, 4. When it's written in this form, it's a little bit easier to get a 0 in this spot. All I gotta do is take the third row and subtract the second row. So 0 minus 0 gives me 0, 1 minus 1 gives me 0, and 2 minus 1 gives me 1, 4 minus 3 gives me 1. I've got all my zeros below the diagonal, which is fantastic. I can now start working on getting zeros above the diagonal. When we're going below the diagonal, we kind of worked from the left to the right, loosely speaking. When we're working above the diagonal, we want to go from the right to the left. What do I mean by that? If our first step is to get these 2 zeros and our second step is to get this 0, our third step is to get the zeros in these 2 spots, and then our fourth step will be to get the 0 in this spot. It's not that you necessarily have to do things in this order, but if you do them in this order, you won't mess up zeros that you already have, loosely speaking. You got to be careful when you're applying these different tools. You don't want to create a 0 here at the expense of one of the zeros that you already have. So by doing things in this order, it'll be easier to not screw up things that you've already gotten perfect. So my goal now is to get zeros in these 2 spots. Great news, I can probably do that all in one step. If you don't feel comfortable with this, definitely do it in 2 different steps. But maybe you can see how if we want a 0 on this line and a 0 on this line, we can just take this row and subtract this row, and then take this row and subtract this row. So I'll leave the bottom row 0, 0, 1, 1 completely alone, and then I'll replace the second row with the second row minus the third row. You might notice that we also could have taken the second row and subtracted the first row, because this one minus this one would also produce a 0 in this spot. But you don't want to do things that way, because if you take the second row and subtract the first row, you'll end up with a -2 in this spot. You'll mess up the zeros that you already have. So you kind of work down as you go on this side and then back up as you go on this side. I'll use this one to get rid of this one, and then I'll use this one to get rid of this one, and then I'll use this one to get rid of this -2. But I'm getting ahead of myself. Let me just do it. The second row, I'm going to take the second row and subtract the third row. So I get 0 minus 0 gives me this 0, 1 minus 0 gives me this 1, and 1 minus 1 gives me 0, and then 3 minus 1 gives me a 2. For the new first row, I'm going to take the first row and subtract the third row. 2 minus 0 gives me 2, -2 minus 0 gives me -2, 1 minus 1 gives me 0, and -2 minus 1 gives me -3. I've got zeros in both of these places, so all that's left is to get a 0 in this place. I can use the second row to create a 0 in this spot, so I'll leave the third row completely alone. I'll leave the second row completely alone. And then for the first row, I'll take the first row and add 2 times the second row. So 2 times 0 is 0, and 0 plus 2 gives me 2. 2 times 1 is 2, and 2 plus -2 gives me 0. 2 times 0 is 0, and 0 plus 0 is 0. 2 times 2 is 4. And 4 plus -3 is +1. I've got all the zeros where I want them. Now it's time to move on to the ones. I already got a 1 in this spot. That's great. I already got a 1 in this spot. That's great. Just need a 1 in this spot and I'm done. To create a 1 in this spot, we'll scale the top row by 1/2. 2 times 1/2 is 1. 0 times 1/2 is 0. 0 times 1/2 is 0. 1 times 1/2 is 1/2. For everything else, I'm just copying it down. I already have my diagonal matrix. And now that I have my diagonal matrix, I have my solutions. The solution to x is the value in this top right-hand corner, 1/2. The solution to y is the value on the far right of the second row, so 2. And the solution to z is the value on the far right of the bottom row, +1. 1/2, 2, and 1 should satisfy all 3 of these equations. You can double check them if you want. Maybe I'll just check one of them. 1/2 times 2 is +1. 2 times negative 2 is negative 4. And in place of the z, I got a 1. Is that equal to the negative 2 that I have on the other side? Yeah, sure is. 2 minus 4 equals negative 2. Maybe I should check the other rows, but I'm confident enough that they'll work. Famous last words, I guess. Keeping these videos somewhat short, I'll move on to another matrix. All right, for this next system of linear equations, I'm going to make a little change here. It actually doesn't change this solution, but I'm going to make this a 6 and this a 6 because it'll make the method a little bit easier, which I think will be more consistent with the level of problems that you'd see in this class. Anyways, note that these equations are already in the right form. We got the x's, the y's, and the z's equal some number on all 3 lines. So we can immediately create our matrix. It would be a 6, negative 3, 2, 6 first row, a 2, 6, negative 1, 11 second row, and a 3, negative 2, 3, 8 third row. Remember, our first goal is to create zeros in these 2 spots, so we'll leave our first row completely alone, 6, negative 3, 2, 6, and then we'll replace our second row with our first row minus 3 times our second row. So 6 minus 3 of these 2's gives me a 0. Negative 3 minus 3 of these 6's is negative 3 minus 18, which is negative 21. And then 2 minus 3 of these negative 1's is 2 minus negative 3, which is the same as 2 plus 3, which is 5. Finally, 6 minus 3 times 11 is 6 minus 33, which is negative 27. Thought the numbers were going to work out nicer. I mean, these aren't the prettiest things in the world, but at least we got our 0 in this spot. What about this spot here? Well, we can zero out this row using our first row by taking the first row and subtracting 2 times the third row. So 6 minus 2 times 3 is 0. Negative 3 minus 2 times negative 2 is negative 3 minus negative 4, which is negative 3 plus 4, which is 1. And then 2 minus 2 times 3 is 2 minus 6, which is negative 4. Finally, in this spot, we got 6 minus 2 times 8. So 6 minus 16, which is negative 10. No obvious reduction that I can do here. So I guess I'll just power through and try to create a 0 in this spot. I can already tell it's not going to be pretty though, because I'm going to have to use the second row. And to use the second row, I'll kind of have to multiply the bottom row by 21. It might be worth showing that as a separate step. If I leave my matrix completely alone on the first 2 rows, and then in place of my third row, I'm going to write 21 times my third row. So 21 times 0 is 0. 21 times 1 is 21. 21 times negative 4 is negative, 84, I guess. And 21 times 10 is 210. So I got a negative 210 in this spot. The advantage to scaling everything by 21 is now I can replace the third row with the sum of the second and third rows, and I'll get a 0 in this spot. First row is still 6, negative 3, 2, 6. Second row is still 0, negative 21, 5, negative 27. But the third row is now 0 plus 0, or 0. 21 plus negative 21, another 0. Negative 84 plus 5, which is negative 79. Negative 210 plus negative 27 is negative 237. You're like, oh my God, these numbers are the worst. I don't want to do this problem anymore. I hear you, but if you happen to notice that 3 times 79 is 237, you might realize this isn't as bad as it seems. I can divide everything in this bottom row by, I don't know, 79 or negative 79. It doesn't really matter. Let's do positive 79 for now. If I divide this by positive 79, I get negative 1. If I divide this by positive 79, I get negative 3. I wouldn't expect you to see this. If I made this a test problem, I'd have to make the numbers work out a little bit nicer so that that was more apparent. But you can check it with the calculator. If I scale this row by 1/79th, it turns into a really nice row. The reason that's really beneficial is because my next step is to get zeros in these 2 spots using this negative 1. Kind of use my bottom row to knock out this position and this position. And this being a negative 1 will make that process a lot easier. I'll leave my bottom row alone, 0, 0, negative 1, negative 3. And then in place of this row, what I'll do is I'll take this row and add 5 times this row. So 0 plus 5 times 0 is just 0. Negative 21 plus 5 times 0 is just negative 21. 5 plus 5 times negative 1 is 5 plus negative 5, which is 0. And negative 27 plus 5 times negative 3 is negative 27 plus negative 15 In other words, negative 27 minus 15. In other words, negative 42. You're like, here we go with the big numbers again. Yeah, but it's not as bad as you think, because in my next step, I'll scale all this stuff by 21. 42 is just 21 times 2. But I don't want to get too far ahead of myself. Remember, my goal is to get zeros in these two spots. So I want to change this 2 into a 0. How am I going to do that? I'm going to take the top row and I'm going to add 2 times the bottom row. This 6 plus double this 0 is just 6. This negative 3 plus double this 0 is just negative 3. This 2 plus negative 2 gives me a 0. And this 6 plus double this negative 3 gives me 6 plus negative 6, in other words, 0. As I pointed out before, I can scale my second row here. In fact, I could scale my first row too if I felt like it. Sure, why not? Let's take the first row and scale it by a third. So I get 6 divided by 3 is 2, negative 3 divided by 3 is negative 1, 0 divided by 3 and 0 divided by 3 are just 0. And then we'll take our second row here and divide by 21. So I got 0, negative 1, 0, negative 2. And then I'll leave my third row alone, 0, 0, negative 1, negative 3. Our first step is to get these zeros. Our second step was to get this 0. Our third step is to get these zeros. Our fourth step is to get a 0 right here. Fortunately, that's going to be really easy. All I got to do is take the top row and subtract the second row. So I'll leave the bottom row completely alone, 0, 0, negative 1, negative 3. I'll leave the second row completely alone, 0, negative 1, 0, negative 2. And in place of the first row, I'm going to write the first row minus the second row. So 2 minus 0 is 2. Negative 1 minus negative 1 is 0. 0 minus 0 is 0. And 0 minus negative 2 is positive 2. I've got all my zeros, so I'm almost done. All that's left to do is get 1s on the diagonals. To make this a 1, I'll divide everything in this row by 2. So I get 1, 0, 0, 1. To make this a 1, I'll multiply everything on this row by negative 1. So I'll get 0, 1, 0, 2. And to make this a 1, I'll multiply everything on this row by negative 1. So I get 0, 0, 1, 3. I've got my matrix in the desired form. Looks like x equals 1, y equals 2, and z equals 3. This video is getting kind of long, so I don't think I want to actually solve this system of linear equations. I think all I want to do is turn this into a matrix. So it'd be 5, 0, negative 2, 8 on the first row, 1, 6, negative 1, 13 on the second row, and 3, negative 2, 0, 2 on the third row. And then leave this as an exercise for you to do. You can try reducing this matrix. It's pretty hard to do, but I think you're capable of doing it. And as a hint, I think the numbers will work out really nicely. I guess I can just tell you. I think x is going to end up being equal to 2, y is going to end up being equal to 2, and z will end up being equal to 1. So if you want a little bit of extra practice, here's a matrix that works out pretty nicely and the answers are really nice. You can do our Gaussian elimination algorithm on this and see if you can come up with these solutions.